Yeah, welcome back. So today I am going to prove an interesting property on characterization of the differential convex functions. So actually there is a result which I am not proving, uh, which is that um, a convex function in the interior of the convex set C is always continuous. Um, just keep this in mind. I am not proving it upfront. Maybe I should write it down once for the sake of record that so this I am not proving. This is theorem 3.1.3 from Bazara Bazara Shereli and Shetty that let S be a non-empty convex set in Rn and let f be the function from S to R be convex, then f is continuous on the interior of S. Now I'll just illustrate what I mean to say here by a simple example that compare these two functions. Both are convex. One is x square, which is nice, continuous, and differentiable everywhere on Rn. Both the functions that I am picking are defined all over Rn, and other is mod of x. So mod of x is continuous everywhere, but not differentiable at x equal to 0. So this function is differentiable uh, everywhere, and the other function is uh, not differentiable everywhere. So this is the interesting result. I will not prove it, but we'll restrict ourselves to uh, right now to functions which are differentiable. I mean, as I have been saying in this course, I am going to worry more about functions which are sometimes twice differentiable, to keep life simple. So, so, so let's prove the this inequality. Uh, there are two parts to this proof, right? Uh, F is convex if and only if uh, f f of z is greater than or equal to f of x plus z minus transpose times of gradient of f of x. So what we are trying to say here, is that if I look at a convex function, okay, if I look at a convex function, let's say like this, and this I take as x, and I draw the gradient line here, and then take any z. So this function is f of z, and I take x here. Then this, let's take this to be the z. So this change is gradient of f of x transpose z minus x. Okay. and f of x. So linear approximation will bring you here. The linear approximation will bring you here, but the function value f of z is greater than or equal to this value. So in other words, the gradient here, the gradient vector supports the convex function from below. Do you see this nice geometry? And hence it can be used for outer approximations of convex functions in algorithm development. So we will not dive deep into that right now, but this is a if and only if result. So what the if and only if result is saying, that if the function f is convex, then the gradient vector will always support it from below, or f of z will be greater than or equal to f of x plus the what you get by linear approximation. Conversely, if this is always true, that f of z is greater than or equal to the what you would get by linear approximation, then the function is convex. So let's start proof by assuming two parts to the proof. First part, I am going to assume that the inequality f of z is greater than or equal to f of x plus gradient of z, a gradient calculated at x times z minus x is true. Okay, this assume that this inequality is true. Then to prove that function is convex. Okay, how do I go about doing this? I go about doing this by first taking 2 points arbitrarily x and y, x not equal to y, in my set C. Then I am going to define a point z as alpha x plus 1 minus alpha times of y. Okay. Now taking this z as a reference point, taking this z as the reference point, I am going to write this inequality to reach x once and then to reach y once. So to reach x once, I can say that f of x is greater than or equal to f of z, z is my reference point, times, where shall I calculate the gradient? At z times x minus z. Then the second time I am going to reach y from z. So f of y will be greater than or equal to f of z plus gradient calculated at z times y minus of z. And now to get a convex function inequality, what I should do? I should multiply this by alpha and this by 1 minus alpha. Alpha coming from 0 to 1. And these inequalities will not change their sign because alpha and 1 minus alpha are positive numbers, so they will retain their sign. And then I add. Then I add these two inequalities. So when I add these two inequalities, what happens to LHS? Alpha of f of x plus 1 minus alpha of f of y is greater than or equal to alpha plus 1 minus alpha of f of z plus gradient of transpose of the gradient calculated at z times alpha x minus alpha z plus 1 minus alpha times of y minus 1 minus alpha times of z. Now let us evaluate what is there in this. So, alpha x plus the lower term 1 minus alpha y minus, taking z as common, alpha plus 1 minus alpha times of z. This is that argument. This is that argument. But this is equal to, what is this? Z itself. And what is this? Again z. So z minus z, which is 0. So therefore this term goes to 0. And hence what do we get? We get that f of z, what is f of z? Alpha z is alpha x plus 1 minus of alpha times of y is less than or equal to alpha of f of x plus 1 minus alpha of f of y, which means that the function is convex. And the corresponding b part of it, that f is strictly convex over C if and only if the above inequality is strict whenever x not equal to z, simply follows by writing this in a strict sense, if the function is strictly, if this inequality holds strictly, then you write this in a strict sense, then you write this in a strict sense, then you add this will become in a strict sense, and then therefore this will follow in a strict sense, which will mean that the function in such a case is strictly convex. Now many of these if and if inequalities, when you try to prove, you usually find that it's like climbing a hill and coming down, or climbing down from a hill and going up. So the point is, you trace back again to the same point on the hill. So coming down the hill is quite easy. Going up the hill takes much more effort. So similarly, usually we find that one part of the if and only if gets proven a bit fast, quickly, and the other one takes a bit of more effort to prove. So in this case, to prove that, assuming conversely that assume that f is convex, and then to prove this inequality is more effort. It requires more ingenuity, and therefore anyway we have to do that both ways. So first assume that f is convex, and let x and z be any vectors in C with x not equal to z, and for alpha in 0 to 1, we will consider the function g of alpha, which is same as f of x plus, which is defined as x plus alpha of z minus of x minus of f of x by alpha, where alpha comes from um, open interval 0, closed interval 1, because we want to avoid division by 0. The whole idea is that we want to avoid division by 0. So in this case, you will find that this is actually a convex combination of x and alpha, because this is alpha z, sorry, x and convex combination of x and z, because this is alpha z plus 1 minus of alpha times of x minus of f of x by alpha. But the way we have written it down, alpha tending to 0, it becomes a gradient in the direction of the vector z minus x. This is anyway a univariate function because alpha is a is a is a scalar. Now we will show that we will show that g of alpha is monotonically increasing with alpha. Interesting. G of will show that g of alpha is monotonically increasing with alpha, and alpha we are restricting between 0 and 1, and is, and of course if the inequality is strict, I, I mean if the function is strictly convex, then it is strictly monotonically increasing in alpha. But let's do the first part, the other one follows very straightforwardly. Then what will this imply? This will imply that z minus x transpose f of x, which is limit of alpha going to 0 from the positive number side of g of alpha. This is this is what I said. This g of alpha we have defined in a specific way that it gives you a derivative information, but only when restricted to the direction of z minus x, which is nothing but z minus x gradient of f of x. So therefore this value should be equal to this value by definition of the gradient. And then if the function is monotonically increasing, then this is alpha tending to 0. So therefore this will be less than or equal to g of 1, will be less than or equal to g of 1. But what is g of 1? G of 1 is, if you put 1 here, then the x and the x cancels out, and therefore this is f of z minus f of x with strict inequality if g is strictly monotonically increasing. And therefore when you take this f of x to the left hand side, see, once we have shown this result, then this follows, and then you take this f of x on the left hand side here. So you get f of z is uh, f of f of z is greater than or equal to f of x plus z minus x transpose f of x, gradient of f of x, which is exactly the result that we want to show if the function is convex. So really speaking, really speaking, our aim is to prove that this is important for us to prove that g of alpha is monotonically increasing with alpha. This is what is important thing for us to prove. So to prove this, consider indeed consider any alpha 1 and alpha 2 between 0 and 1 such that alpha 2 is greater than alpha 1, and let us define alpha bar as alpha 1 by alpha 2 and z bar as convex combination of x and z. This is same as this is same as alpha 2 times of z plus 1 minus alpha times of x. The way we have of course write in this particular way is because we say that we are taking a step of alpha 2, the larger of the two, in the direction of z minus x, and this gives me a point called z bar, which is on the line segment joining x and z. So z bar is somewhere here, and I have taken a step of alpha 2 in the direction of z minus of x. Now we have, by convexity of f, that f of I'm sorry, f of x plus alpha bar z bar minus of x is less than or equal to alpha bar of f of z bar plus 1 minus alpha bar of fx. This is simply by writing this, recognizing that this is alpha bar z bar, which gives me this term, plus 1 minus of alpha bar times of x, which gives me this corresponding term. And what is it that I am using? I am using the condition that the f function is given to be convex. Or I can write f, I'm sorry, or I can write that f of x plus alpha bar z minus x, and now I am going to take this f of x term here, this f of x term on the left hand side. So I am going to take minus of f of x, and then I am left with alpha bar f of z bar minus alpha bar f of x. So therefore I am going to divide whole thing by taking alpha bar common. I am going to divide everything by alpha bar, and then this becomes less than or equal to f of z bar minus of f of x. See, the idea is, though it may look difficult, and it is actually difficult to also give intuition to it. People get proofs in after a lot of effort, and once they have got the proof, then to ask the question, where was the intuition? Sometimes it's a bit difficult to get it, but you should try to understand these proofs and still try to see the intuition behind it somehow or other, so that you can use this and practice these proofs, so that when time comes for you to prove something, you are not found wanting. One intuition, of course, I can very clearly tell you here is that we are trying to, because we want to get g of alpha, we are trying to write this in a form of g of alpha, and then we are going to look at limit alpha tending to 0. So we are trying to get the derivatives in the direction of z minus x, and therefore we have chosen these terms in some particular sense. This is part of the intuition, and the part of the intuition here is that because we want to show monotonic result, that g of alpha 1 is less than or equal to g of alpha 2 if alpha 1 is less than alpha 2. So therefore we had to choose alpha 1 less than alpha 2, and of course everything we want to keep in the 0 to 1 level, so that convexity definitions can be used, and therefore we cooked up a smaller number out of the two by taking a ratio. So uh, this much only I can expand on the intuition. The rest I will have to leave it to you. Now, substituting the definition of alpha bar is equal to alpha 1 by alpha 2 in this equation, in this above equation. So where are the two substitutions going to happen? One substitution is going to happen here. So I'm going to just cut this here from here, copy, and maybe paste it here. And now what I'm going to do is, this is, for this I have to substitute alpha 1 by alpha 2. So I will take alpha 1 here, and alpha 2 goes 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 here, and then since the alpha 2 has gone here, I can bring it at the dividing both sides, dividing both LHS and RHS by alpha 2 a positive number. I will get this thing here, and now let me look at what is this is z bar, because this is z bar, this is z bar, so this has to be z bar, and so this has to be z bar. Now let me look at what is alpha bar z bar. Alpha bar is alpha 1 by alpha 2, and substitute for z bar. What should be substituted for z bar? X plus alpha 2 into z minus x, or in other words, this will become alpha, so this will become alpha, this will become x of plus alpha 1 into z minus of x. So alpha bar into z bar minus of x. This is what we are looking at, and so the x and x will cancel out here, and this alpha bar will cancel out with this, and so you get this term as alpha 1 into z minus x, to which we are adding f. X is already present here. So now look at the simplified inequality. Look at the simplified inequality. F of x plus alpha 1 z minus x by alpha 1 is less than or equal to, for substitute for z bar x plus alpha 2, what is z bar? X plus alpha 2 z minus of x, z minus of x minus of fx by alpha 2, or since alpha 1 is less than alpha 2, what we wanted we have shown. We wanted to show that g alpha 1 is less than alpha g alpha 2, and already alpha 1 was chosen to be less than alpha 2. Now g alpha 1 has become less than or equal to g of alpha 2, which shows that the function is monotonically increasing in alpha, and hence the said result follows. And all the above inequalities become strict if the function is strictly convex. So therefore the b part also automatically follows. For the what is the b part follows automatically? By that what I mean? By that we mean that we are showing that if function is strictly convex, then f of z is strictly greater than f of x plus z minus x transpose f of x. So we have proved this theorem, and as I said, this is a very nice geometrical property this theorem gives us, which is to say that the linear approximation is the support from below and an outer approximation for the convex functions. Uh, this with this we will take a break. Thank you.